Hi, my name is David Lennick, and I'm going to be presenting on container-based Internet of Things architecture pattern kill switch, written by myself, Dr. Azim, Dr. Liscano at the Ontario Tech University, University in Ontario, Canada, and we're presenting at the IEEE International Symposium on Real-Time Distributed Computing 2020. So to give a brief overview of what we'll be discussing today, so we'll go through some definitions. We'll give a brief overview of what the problem area we're addressing with the pattern, and we'll give a quick scenario just to give some further illustration. We'll describe what our pattern is, give an example implementation of it, and then we'll give a brief conclusion. So some quick definitions. So what is a design pattern? So a design pattern is just a way to solve a common, narrowly focused problem, typically in the computer field. So in object-oriented programming, an example is the factory pattern. So the problem here that we're addressing is we don't want to create specific instances of a class immediately, or we have to create an instance of the class at runtime, right? So given some produced set of classes that use a predefined interface, a factory object then can be extended to create any type of the produced classes, as long as they're using that same interface. So this general idea is what we're dealing with, development of these types of patterns, right? So what is a container though? So containers are a type of virtualization. Traditionally, virtualization has been accomplished with hypervisors, which use bare metal resources to subdivide that computer up and then run imaginary computers called virtual machines. But the problem with traditional virtual machines is that they tend to require more resources, as everything from the base system all the way up through a file system and the operating system all have to be virtualized, and it's very difficult or impossible to share resources between virtual machines. So containers are a different form of virtualization, and as they use Linux namespaces to separate processes from one another, and C groups to limit the resources available to a specific namespace. So and then these containers also use the base operating system Linux kernel amongst themselves, right? So they all use the same kernel, they use the same code base, which makes them much less resource intensive, and as a result also use a lot less compute resources. So this allows containers to be used in a variety of ways. One of the most notable is that they are very similar to how one might use objects in object-oriented programming, and a particular instance of a container platform is called Docker, and this platform is used to create and run container images, which then are used to create containers, and then it allows these containers to all be networked together. So just a quick note on real-time containers. So this pattern is the one we're talking about in our talk here today, is of particular interest when combining the concepts of real-time computing and real-time Linux capabilities with containers themselves. So containers use the base Linux distribution's kernel. So that also means that if the kernel has real-time capabilities enabled, containers are able to utilize the real-time clock as well. So some more definitions, container patterns. So Birds and Oppenheimer describe and formalize a set of emergent design patterns for container-based systems, and it was from 2016, and to our knowledge, there hasn't been too much work done on container patterns since then, or at least formally. So they describe a few different types. So a single container pattern, meaning you have one container. Where does a container stop? Where does a container end? What's the life cycle of a container? How do you manage that single container? And other operations like that. They also specify a pattern, a set of patterns for a single node, multi-container applications. So that means, you have one computer, you have a bunch of different containers running on them. What can you do? So one of the types of patterns that is fairly well known is called the sidecar pattern. So a sidecar pattern is like you have a single container, such as a Node.js server, and you have a sidecar pattern that then accentuates or augments the functionality of the core container, right? So an example might be if you have a GitHub, a website, for example, right, and it's just serving up static pages, you might have a sidecar container that pulls from a GitHub repository and updates the static files on the main container. So the last type of pattern grouping that they describe is called multi-node application patterns. So this involves multiple nodes running one-to-end containers. So this is where we get into more traditional or more well-known distributed computing patterns and systems. So you get things like fan out and, you know, a leader election and that type of thing. So the problem here, though, is when you have a virtualized system, you have something called multi-tenancy. So multi-tenancy is when you have a bunch of different containers or a bunch of different virtual machines running on the same system. So this has serious security and anomaly implications. So because containers are isolated units, there should be some method of altering containers as discrete units to modify application functionality. So using the containers themselves to modify how an application works. So given some external event, the container-based application should be able to adapt to operate using a predefined set of critical functionality without significant alterations or modification to source code. That is, supersets and subsets of application functionality should be able to operate and exist in multiple modes of operation. So what we're trying to say is that given a set of containers, there should be some way to make sure that critical functionality of these of an application is segmented out into separate containers, and there should be some way to make sure that the critical application functionality is retained. So to give an example, we have a smart car, and this smart car is connected to the internet, and the different subsystems of a car's ECU are all kind of simulated or run on a single SoC in containers, right? So in our scenario, at the top, we have a firewall and a gateway out to the internet, and we have in red the different actual required functionality for the vehicle, right? So the drivetrain, you know, acceleration, GPS, and those types of things. So in our case, our platform is running on Docker, and we have an external security system kind of listening for attacks. And in our case, the system has been attacked, and it's at the gateway right now. So because we have something happening, all of the containers in blue should be immediately killed to prevent, you know, the surface area, and therefore, in this case, connection to the internet. So that means only the critical car's functionality of steering and, you know, running are actually available. So this is where our kill switch pattern comes in. So via some external event, a set of containers providing some set of functionality and their individual states shall be alterable at runtime to provide some reduced minimum or altered set of containers and functionality. The application architecture resulting from accounting for this pattern consideration should have the ability to enable multiple modes of overall application operation. Here's a quick notion here. So just to clarify some things, so we have a set of containers, and we also have a set of functionality that is associated with these containers, and these all kind of these two things create a application called X. So in altered state mode, given some event, let CAR be a subset of CA, let FAR be a subset of FA. So then, as a result, the subsets of CAR and FAR are combined to create an application with X with reduced functionality. So in order to test this out to see if it was actually feasible, we modified the Docker API to add this kill switch in. So we tagged containers as critical, and all others are assumed to be non-critical. And when the API was triggered, it killed all unessential containers. And you can see on the right-hand side, we have a activity diagram showing the basic logic flow of how the system will eventually get to its target state. And we also performed the same functionality in external Go script and checked the performance between the two, and there was little to none because they were both running on the same little to no difference between the two because they were both running on the same system, which is good. But if you were to have the external script being triggered from outside the system, such as if you have an orchestration system, there would be significant performance overhead with the network latency to trigger these multiple API calls. When in comparison to directly implementing the API into the Docker engine, there's a significant reduction in the IPC between the orchestration and the container platform node, as well as it's more likely that it's going to be executed, right, because it's just one call being sent to the platform. So we chose not to implement a specific type of architecture in this case because we wanted it to be as generic as possible. We wanted to just see, if applications can, or if containers can be killed, in a reasonable way that would be reflective of the pattern. And who would have thought it's possible. So to conclude, we found that the emergent pattern is indeed feasible and should be used in conjunction with other frameworks. And we hope this is a step towards better embedded Linux IoT application frameworks in development, utilizing containers as building blocks. And we also stipulate that container patterns are a major potential research area, much like service-oriented architecture or object-oriented programming concepts have been. So thank you very much for your time. If you have any questions, feel free to email me at david.lennick@ontariotechU.ca.